of the natural systems where it appears, namely sunflowers and some simple models thereof. You may notice that that's not actually a sunflower. It's the best I could do in the neighborhood. It's kind of like reminiscent of a sunflower, maybe. But I chose this topic because I've heard a lot of casual conversation about the golden ratio, all the places it appears, and I didn't really know what to believe because I had never gone in depth and done the research for myself. So I'm hoping some of you are in a similar situation. So I'm going to start off by going over some of the mathematical properties that make the golden ratio interesting. And then I'm going to introduce some systems in nature where it's exhibited, namely sunflowers and some lab models of sunflowers that are kind of a little bit simplified. And then I'm going to explain the pretty simple mechanism that can generate the golden ratio as it's exhibited in sunflowers. So the golden ratio, which I'm calling gamma, is defined by this equation here. Namely, it's the positive solution. It's very intimately related to the Fibonacci numbers in that it's the limit of the ratio of consecutive Fibonacci numbers. These are like 1, 1, 2, 3, 5, 8, etc. You probably are familiar with those. Also, the golden ratio is the most irrational real number in that it's worst approximated by rational numbers. Now, I can't really talk about the golden ratio without mentioning that it's considered to be aesthetically pleasing. I don't know if this hairy arm counts, but anybody here have golden ratio tattoos? No? Yeah, I can't deny, like, the thought has crossed my mind. It's a pretty popular tattoo basis for nerdier groups of people. Like, there's a lot of different examples online. It's pretty easy to find. But it also shows up in nature. This is given pretty frequently as an example of the golden ratio in nature. People claim that nautilus shells exhibit logarithmic growth with a golden ratio growth rate. But in general, I found that it's just not true. And that's actually a kind of recurring theme with a lot of the more commonly known examples of the golden ratio in architecture or like animal bodies. A lot of these things are disputed, to say the least. So I'm sticking to things that are more well-studied, namely the growth of sunflower seeds. So believe it or not, all those seeds grew one at a time, and the angular separation between consecutive seeds is related to the golden ratio. And that feature isn't unique to sunflowers. It holds in a lot of other plants in the growth of like leaves or seeds or whatnot. What I mean when I say that the angular separation is related to the golden ratio, I mean that it's equal to this phi, which is defined by setting the ratio of the red length to the blue length equal to the ratio of the blue length to the circumference of the circle. Now, there's a few key things to note about the physics of sunflower seed growth, in my opinion. First is that the seeds start on the surface of a cylinder, and they are located sequentially in the axial direction, like they form one on top of another. Also, very importantly, there's a repulsive interaction between seeds, which is due to the fact that the presence of a seed reduces the concentration of a chemical, which is required for growth of seeds. So what that means is that seeds tend to grow in open spaces as far as possible away from present seeds. Now, biochemists are actually quite interested in this phenomenon, and they have some very complicated models that go way beyond these facts. But as you can probably imagine, physicists aren't too interested in that. And in fact, some people at Penn State University have designed a kind of a toy model of a sunflower, which they call a magnetic cactus. And what I mean by that is they locate some magnetic dipoles on a cylindrical shell with some radius r, and they're evenly spaced in the axial direction, and they're allowed to move only in the azimuthal direction around the cylinder. That might be kind of hard to imagine, so here's a picture. As you can see, they're little discs that can rotate azimuthally, but they're fixed in the other dimensions. Now, these guys at Penn State successfully reproduced the golden ratio angular separation. But that on its own, it doesn't seem that like amazing or informative to me. It's just like they got the final result. And I think that's due to the fact that they had only a fixed axial spacing, because obviously they had a physical system. So I thought maybe it'd be a good idea to do a numerical model of this experiment where instead of having a fixed axial spacing, we can let the axial spacing vary. So we start from the same idea, repulsive particles located on the surface of a cylinder, evenly spaced. But now we allow the axial spacing to vary, and we determine the ideal angular separation between adjacent axial particles. The way I did that was just by assuming it was a purely nearest neighbor interaction. So I started, I calculated all the distances and found the nearest neighbor distance, and then maximized that as a function of phi. And here are the results. So for large axial separations, much greater than the radius, obviously the nearest neighbor is just going to be the next axial particle, because the radius is, I guess I can maybe, is there no chalk? Anyway, if A is much greater than R, where A is the axial separation and R is the width of the cylinder, then the next one up is going to be much closer than the second one up, if A is large compared to R. So then in order to maximize the nearest neighbor distance, the angle will be pi, so that it'll be located on the opposite side of the cylinder. So for large A, we see that the angle is indeed pi. That's phi 1. But as A decreases through 2r over root 3, you have a bifurcation because the nearest neighbor becomes the second nearest axial neighbor. That's the nearest neighbor in 3D space, is the second nearest neighbor along the axial dimension. And at that point, the angles begin to change, and they drop down asymptotically toward phi 2, which is 2 pi over 3, until a similar thing happens, where the third nearest neighbor in the axial dimension becomes the nearest 3D neighbor. And it bounces back and forth until it asymptotically approaches the golden ratio in the limit of n going to infinity, where this is just the ratio of consecutive Fibonacci numbers, like I said before. So in the limit, this is going to be 2 pi over gamma plus 1, which is just the golden angle, which I defined before. So I'm going to quit out of this quickly, because maybe I can explain that a little bit more clearly with the video. So I define this kind of potential, or something analogous to a potential, which is the inverse nearest neighbor distance, because I'm trying to maximize the nearest neighbor distance. So when you start off at large A, the minimum is here at pi, and then it bifurcates, and it's bouncing back and forth now between phi n for larger n, and asymptotically approaching the phi golden angle. Should I do that one more time, or is that clear? It's probably clear. All right. So in conclusion, I'd just like to say that the golden ratio is pretty awesome. It's got all sorts of interesting mathematical properties, and also it's pretty ubiquitous in nature. It shows up in all sorts of different contexts. Importantly, it shows up in sunflower seed patterns. And in fact, we can derive the golden angle separation of those sunflower seeds from a kind of a first principles model that's quite simple, just assuming nearest neighbor repulsion between the seeds. And that gives us the asymptotic golden angle, which is pretty cool, I thought. So thank you very much. Yeah.
So underneath your graph on a previous slide, you have a formula for theta n.
Yeah.
So theta is...
Phi n is like the value to which this is asymptoting. So right now it's asymptoting toward phi 2, and then at this point it begins asymptoting to phi 3, and so on. And then phi 5, 8, it's Fibonacci.
That's the optimal distance spacing between neighbors?
It's not for any spacing that you get to, but like the optimal spacing is this curve. But the curve is approaching phi n until you have a critical value of a where the particle directly above the particle you're considering becomes closer than the other nearest neighbor. actually, now that I have a second, I can show you what I mean by this. Okay, so you have the guy here, and a guy here, and a guy here. Obviously, this is closer than that. But as we bring that closer, as we reduce A, we're going to have some critical value where this distance is less than this distance. And that's where those bifurcations happen. And it happens for different values of the spacing, too, not just for pi. Yes?
You said that this golden section is the most irrational real numbers. What does it mean?
I thought someone might ask that. This is what it means. This is how they define goodness of a rational approximation. It's what they want to do is have a good absolute distance, but also a small denominator. So, like, there's no approximation for the golden ratio that's better than 22/7 is for pi by this metric. Yes?
So, I mean, you compared it to pi, but is there like a proof that it has to be maximally?
Yeah, in fact, it's proved that there's a class of numbers of the form a plus b phi over c plus d phi that are all tied for worst in terms of this rational closeness. And it turns out that numbers like pi and e and transcendental numbers are actually surprisingly close to rational numbers. They're really well approximated. And it's simple things with square roots and stuff are really bad. Like root 2 is pretty bad.